There are materials we admire, and then there are materials we depend on without realizing it. Tungsten belongs to the second category. It doesn't shine like gold or bend like copper. Instead, it sits quietly inside engines, cutting tools, electronics, and spacecraft, doing jobs no other metal can survive. Without tungsten, aviation would stall, industrial manufacturing would slow to a crawl, and entire sectors of modern technology would simply stop working. And yet, despite its importance, tungsten remains largely invisible to the public. Few people know where it comes from, how it's made, or why nations treat it as a strategic resource. What makes tungsten special isn't just one property, it's the rare combination of extreme heat resistance, strength, density, and endurance, qualities that push engineering beyond normal limits. Why tungsten is physically unmatched. On the periodic table, tungsten is element 74, a transition metal with properties that read almost like exaggeration until you test them. Tungsten has the highest melting point of any metal on Earth, reaching approximately 6,192 degrees Fahrenheit, 3,422 degrees Celsius. At temperatures where most metals soften, deform, or vaporize, tungsten remains solid. This alone makes it indispensable in environments defined by extreme heat. But temperature resistance is only part of the story. Above 3,000 degrees Fahrenheit, tungsten also exhibits the highest tensile strength of any pure metal. Combined with its exceptional hardness and density, this allows tungsten to resist wear, deformation, and mechanical failure under conditions that destroy conventional alloys. These traits are why tungsten is chosen not for convenience, but for necessity, where tungsten comes from. Despite its industrial importance, tungsten never occurs naturally as a pure metal. It's locked inside mineral compounds deep within Earth's crust, primarily in two ores, wolframite and scheelite. Wolframite is a complex mineral composed of iron, manganese, and tungsten. Scheelite is calcium tungstate, visually distinct but equally valuable. Extracting tungsten means first finding these ores, which are often buried deep underground. Major tungsten-producing countries include China, Vietnam, Russia, and Canada, each holding strategically significant reserves. Because tungsten is rare and unevenly distributed, access to it has long been tied to geopolitical influence and industrial security. Mining tungsten. The journey of tungsten begins with exploration. Geologists identify ore deposits using geological surveys, sampling, and modeling to determine whether extraction is economically viable. Because tungsten deposits are often narrow and discontinuous, accurate mapping is essential before large-scale mining can begin. Once a deposit is confirmed, mining begins, either through underground mines or open-pit quarries, depending on depth and terrain. Tungsten ore is exceptionally hard, and extracting it requires powerful drilling equipment, reinforced cutting tools, and carefully controlled blasting to avoid excessive dilution with waste rock. This is demanding, dangerous work. Thousands of tons of rock are moved daily under strict safety standards, with heavy machinery operating around the clock. Ventilation, ground support, and water control are constant challenges. But raw ore is only the beginning. Most of what's extracted is still waste rock, from rock to concentrate. After extraction, tungsten ore is transported to processing plants, where physical separation begins. The goal is to isolate tungsten-bearing minerals from the surrounding material while minimizing material loss. First, the ore is crushed and milled into a fine powder to liberate individual mineral grains. Then, a combination of gravity separation, magnetic separation, and flotation techniques is used. Gravity methods are especially important because tungsten minerals are significantly denser than most surrounding rock. Each method exploits differences in density, magnetic properties, or surface chemistry. The result is a tungsten concentrate containing roughly 60 to 70% tungsten trioxide, WO3, a critical intermediate form that can be economically refined. At this stage, the material is no longer rock, it's an industrial feedstock. Chemical refining. Producing pure tungsten from concentrate requires a tightly controlled metallurgical process. The concentrate undergoes alkaline leaching to dissolve tungsten compounds, while separating unwanted impurities, such as silica and sulfur-bearing minerals. This solution is then processed through chemical precipitation to form ammonium paratungstate, APT, a highly purified and standardized compound used across the global tungsten industry. The consistency of APT allows manufacturers to produce tungsten products with predictable performance. A PT is roasted to produce tungsten oxide, which becomes the direct precursor to metallic tungsten. The final transformation happens in high-temperature furnaces, where tungsten oxide is reduced in a hydrogen atmosphere at temperatures between 2,000 and 3,300 degrees Fahrenheit. Oxygen is removed, leaving pure tungsten metal as a fine powder. Powder metallurgy. Unlike many metals, tungsten is rarely melted and cast due to its extreme melting point and brittleness in liquid form. Instead, it is shaped using powder metallurgy, a process that preserves structural integrity while allowing precise control. The tungsten powder is pressed into molds under immense pressure, forming rods, bars, or blanks with uniform density. These shapes are then sintered, heated to extremely high temperatures in a hydrogen atmosphere just below tungsten's melting point. During sintering, individual powder particles bond together at the atomic level, eliminating internal voids and increasing strength. The result is dense, solid tungsten with exceptional mechanical integrity. This method allows precise control over grain size, strength, and performance, making tungsten suitable for applications where failure is not an option. Tungsten carbide. One of tungsten's most important transformations is into tungsten carbide. By combining tungsten with carbon and using cobalt or nickel as a binder, engineers create an alloy that ranks among the hardest man-made materials on Earth. Tungsten carbide is used to manufacture cutting tools, drill bits, end mills, lathe inserts. These tools can slice through hardened steel, titanium alloys, and rock formations thousands of feet underground. Modern manufacturing, mining, and oil extraction depend on them entirely. A single pound of tungsten can become a tool that outperforms tons of conventional steel, military, aerospace, and high-heat applications. Tungsten's density and hardness also make it invaluable for military applications, including armor-piercing ammunition, protective plating, and counterweights. Its ability to maintain structure under extreme impact gives it unmatched penetration characteristics. In aerospace, tungsten alloys are used in jet engines, turbines, and high-temperature components. Alloying other metals with tungsten dramatically increases their heat resistance, allowing engines to operate hotter and more efficiently. Few materials can survive these environments. Tungsten was designed for them: electronics, medicine, and everyday uses. In electronics, tungsten is everywhere, often unseen. It's used in incandescent light bulb filaments, welding electrodes, electrical contacts. Its high melting point and conductivity make it ideal for components exposed to intense heat. In medicine, tungsten's high atomic number allows it to block X-rays effectively. It's used in X-ray tubes and radiation shielding, offering similar protection to lead, but with far lower toxicity. Tungsten's density also makes it useful for counterweights in aircraft, race cars, and yachts, and even for scratch-resistant jewelry. Rarity, production, and strategic importance. Tungsten is one of the rarest elements in Earth's crust. Economically viable global reserves are estimated at 3 to 3.5 million tons, far smaller than common metals like iron or aluminum. Annual global production fluctuates between 85,000 and 100,000 metric tons, including both mined and recycled material. These numbers highlight just how limited the supply really is, and why tungsten is considered a strategic resource worldwide. Here's the part few people talk about. Tungsten is one of the most efficiently recycled metals on Earth. Up to 40% of all tungsten used globally comes from recycled sources, primarily worn-out carbide tools. Instead of being discarded, these tools are collected, processed, and transformed back into usable tungsten material. Recycling eliminates the most energy-intensive steps of production: mining and initial ore processing. It significantly reduces costs, energy use, industrial waste, and greenhouse gas emissions. In a world facing resource constraints, tungsten's recyclability may be its most important hidden strength. Why tungsten is the metal of the future. Tungsten doesn't just support modern civilization, it defines its limits. Wherever heat, pressure, wear, or time push materials to failure, tungsten holds the line. It's rare, difficult to produce, and impossible to replace. And as technology demands stronger, smaller, and more resilient systems, tungsten's role will only grow. The metal of the future has already been here all along. quietly holding everything together.